And finally, I want to show you a little bit about spectral clustering, which is kind of more mathy and kind of more complex, so it will take us a little longer here, but let's have a look at it. So spectral clustering is a completely different way of thinking about clustering. In the end, we'll see that it's also again a kind of mixture of partitioning based methods like k-means and somehow density based methods, but anyway. So the view of the whole problem is now a kind of graph partitioning view. So we model the data by a so-called similarity graph. And a graph, of course, has vertices, the nodes, which are the data objects, and and edges, which are the similarity between two nodes. Yeah? So the edges are actually weighted in that case. So the question is how to actually model the weights here, or the similarity, the edges here. So there are usually you have, of course, if you have n vertices and data objects, you have n squared edges, but there are some variants that just take the so-called epsilon neighborhood graph. So only the vertices, the objects that find themselves in a distance of epsilon are only those edges are actually recorded in the adjacency matrix, yeah, and all the other edges are not considered, so to say. Yeah, so you can use here epsilon neighborhood graphs, or you can use the k-nearest neighbor graph, which is then, of course, where you only consider edges between the k-nearest neighbors of objects, yeah, and so on. And of course, the so to say worst case is that you just take a fully connected graph. Yeah? So there's just variance in terms of how or what kind of edges you actually allow between the nodes, the vertices, the objects. Yeah? So vertices in the graph, you see here a graph. So here we have the vertices 0, 1, 2, 3, 4, 5. Those are actually 6 objects, data objects. And we have vertices between them. And you see that in that case, it's the 3 nearest neighbor graph. So each vertex is connected to its 3 nearest neighbors, and the weights of the edges are depicted here. Yeah, and then the idea is that we cluster the data by just partitioning this similarity graph. Yeah? And of course, we can partition that or cut the graph in many different ways. And probably the most intuitive one is to find a global minimum cut. So minimum cut means that if we cut the whole thing, then we get two connected components that are not linked with each other, of course, yeah. And so that is a minimum cut, and a global minimum cut is then that the sum of the edges, of the weight edges, of the weighted edges, of the edge weights. Now the sum of the edge weights are minimal, are minimized. Yeah. However, that has some kind of drawbacks, because first of all, looking for a global minimum cut, we only consider it at the end inter-cluster edges. So we try to cut those that have a high weight, yeah, and it tends to cut out small vertex sets from the graph. Yeah, so it's probably better to cut out this one than this one here, yeah, for the overall costs, and that's actually not what we obviously want. Yeah, and the second problem is that if we try to find a minimum cut, any minimum cut is of course just a cut into two partitions, into two clusters. Yeah, and of course we can do that multiple times, but then that would be a locally optimized cut, of course. Yeah, because the first cut will be optimal for the whole graph, and then the second cuts would be optimal for the subgraphs, and so on and so on and so on. Yeah. So instead of just doing that, we try to find a balanced multi-way partitioning. So this is kind of the idea here, that we have a multi-way partitioning, a multi-way cut, not only in two cuts, in two partitions, and that the whole thing is more or less balanced over the entire costs over the entire weights of the edges. Yeah. However, such multi-way cuts, multi-way partitioning problems are typically NP hard. So in that case, we have to come up with some heuristics, some approximate solutions, because the exact solutions are I mean, they are computable, but they are not computable in reasonable time typically. Yeah? So we have to come up with heuristics. So what's coming up actually is heuristics about how to solve that idea of computing a balanced multi-way partitioning of these similarity graphs. So spectral clustering is about given an undirected graph with weighted edges, and we have the weighted adjacency matrix of the graph, which is W. Yeah, and we also compute the so-called degree matrix, which is this one here, which is a diagonal matrix, and we just compute for each node. So on the diagonal of this matrix, we have the entries for the corresponding node. For the corresponding object. So what we do here in this matrix is we compute at the diagonal the sum of all the weights from this node to all the other nodes in the weighted adjacency matrix. Yeah, so that is the simple one. So here you see an example. So for example, the weight of the edge between 2 and 3 is 3. So we have vertex 2, vertex 3, and the weight here is 3. Yeah, so the entry in the adjacency matrix, which is a n times n matrix for n objects, would be 3 in that case. Yeah? And the weight between 2 and 5 is 0 because we don't have an edge between those two. Yeah? So in the case we have no edges, we have a 0 entry in the weighted adjacency matrix, and the degree here, for example, for 2 would be the sum of all the weights from 2 to all the other nodes. So that would be 2 plus 3 plus 2. Yeah, that would be 7 in that case for the node 2. Yeah, so the entry in the degree matrix for 2 would be 7. Yeah, which is the sum of the weights of all the edges going out of 2. Yeah? And now the aim is we want to partition the graph, as said before, into k subsets, minimizing a function of the edge weights between and within the partitions. So very, very similar to the idea of partitioning algorithms. We want to minimize the in-between, the intra-cluster weights, and we want to maximize the inter-cluster, in-between cluster weights, so to say. Yeah? So very, very similar as k-means, for example. And you will see that we use k-means, but not yet. Yeah. Sorry, because we still have to do a little bit of workaround. And the first workaround here is this indicator vector for a given cluster. Yeah, so we want to have k clusters, so we have k indicator vectors telling us which objects are in that cluster actually. Yeah, so for a given cluster C, the indicator vector just states for each object in our data set whether or not this object is in this particular cluster C or not. Yeah, and it's very easy to actually model that, because the entry I, so the object I, has a 1 if this object is in that cluster C, and a 0 if this object is not in cluster C. Yeah, so the cluster or the indicator vector of cluster C has n entries. Yeah. And one entry, the corresponding entry I, is 1 if object I, vi, you see here, vi is the vertex or the object I, is in the cluster C, and else it's 0. Yeah? So we have k indicator vectors, and each indicator vector has n entries. And we need this so-called Laplacian matrix, which is just D minus W. So D, once again, is the degree matrix here, yeah? And W is the weighted adjacency matrix. That is called the Laplacian of the graph, Laplacian matrix, or short Laplacian of the graph. Yeah? And now we can take the following function as a kind of optimization function. Why that is the case, we see if we have a look at that. So first of all, the function is f times the Laplacian, so the indicator vectors, times the Laplacian times the indicator vectors transposed. Yeah? So f is the matrix built of the k indicator vectors. So it's an k times n matrix, so to say. Yeah? And that actually is or equals this term here. We will see on the next slide just in a couple of minutes why that is actually the case. But if we have a closer look at this part here on this side here, we will see the following effect. Well, fi minus fj means, well, if object I and object j are in the same cluster, it's it's a 0, yeah. Then the weight doesn't play between those two objects, doesn't play any role in this sum here. Yeah. If fi minus fj is so if they are in different clusters, then that is obviously +1 or -1, depending on whether this is 0 or this is 0 and the other one is 1. Yeah? So fi is the entry of this one here. Yeah. So if I and j are in the same clusters, they have obviously the same ones and the same zeros. Yeah. So in that case, this one here is 0, and if they are in different clusters, they have different ones and different zeros. So in that case, this minus here gives us +1 or -1. Squared means we get 1. Yeah? So we take the sum of all the weights between objects that are in different clusters. Yeah? So the weights of objects that are in the same cluster will have times 0, yeah? And all the others will have times 1. So we just sum up the weights of all the objects I and j that are in different clusters. Yeah? And obviously, this sum here is small if f corresponds to a good partitioning, obviously. Yeah? So given an indicator vector, the function measures the weight of the intercluster edges. Yeah? And that's absolutely something which is easy to measure, actually. Yeah? So yeah, since L is positive semi-definite in that case, we have this function here is greater or equal than 0. Yeah? And of course, we try to minimize FL, F transposed. Yeah. So there was a kind of just coming up into my mind. Why should be that small if that is a good partitioning? Because we're talking about a similarity graph and not a distance graph. Yeah. So the weights are actually similarity functions. Yeah. So the smaller the better. Yeah. Sorry, the higher the better, the smaller the higher the distance is. Yeah? So that's why a small value of this one here would be better than a higher value, and the whole thing should be minimized.